Hi folks, welcome back to Math with Captain Rod. I'm making this video here to go through an example of how to use Riemann sums in the limit process to calculate the exact area under a curve. I've kind of outlined the process over to the right, and it's kind of a four-step process. Really, I think I missed one. I'm going to go back and put a step 0, which is going to be draw rectangles. Basically, this is your setup. Then Step 1 is going to be find a formula for the x sub I. Step 2, find a formula for the a sub i's. Step 3, write out a formula in terms of summation. So for example, the total area will be approximately equal to the sum from y equals 1 to some number of your a sub i's. And then step 4, you can make this approximation exact by driving the number of rectangles to infinity through the limit process. So you take the limit as n goes to infinity of this ratio, and you get identically total area under the curve. So let's go ahead and get started and see what this looks like. So you start out with these things by using your rectangles here. And I'm going to go ahead and draw my first one like this, second one like this, third one like this. Now, you got to think kind of abstractly here. We're not going to use 3 rectangles or 5 rectangles or 6. We're going to start and we're just going to say n rectangles, whatever that is. I drew these kind of extra large just to so that we can very clearly see what we're talking about. You know, there could be 3 of them. You know, the way I've drawn this, it looks like there'd be like 4 or 5. But what you have to realize is it could be 50, it could be 100, it could be 1,000. These are just kind of expanded so we can take a look at them. Also, you notice I just went right to an upper bound estimate. It doesn't matter at this point whether you use an upper bound, lower bound, or midpoint, because down the road, when we take this limit as n goes to infinity, all answers will converge to the same thing. It only matters, you know, how particular you are here only matters when you're using a finite number for n, and the larger n is, the less it matters, basically. So this tends to be a nice, easy way to set up our formulas here. So I have done step 0, drew some rectangles. I'm going to go ahead and now start thinking about the x sub i's we're going to need. We're going to need this one, this one, this one, and a bunch more, but I'm just going to leave those 3 for now. Now, this is my first rectangle right here. There's my second, my third, and it goes on and on and on. Now, you'll notice that this guy here is 1 delta x when I is 1. And here, this one is 2 delta x when I is 2. So what I'm going to do is make my formula here. My x sub I, in general, is I times delta x. This part will depend on how you set up your rectangles. Had we used lower bound or midpoint, you'd have something slightly different. I just tend to use whichever one sets my x sub i's up as quick as possible, or as easily as possible. All right, we're going to need the delta x. Now, delta x is always upper bound minus lower bound divided by n. In this case, that's going to be 1 over n, right? We're taking this distance dividing by n rectangles. All right, so kind of updating my x sub I, that's equal to I over n when we take that and sub it there. All right, now we need, all right, so this is, I'm going to call that checked off. Drew my rectangles, did my x sub i's. All right, formula for the a sub I. So a sub I now, I want a formula that's good for all of them. In general is the function value at the appropriate x location times delta x. So in this case, that's going to be 3 times I over n squared. There's my function value. I got that by taking my formula for x sub I and subbing it there. Right? Then times delta x. So this needs to be multiplied by I over n. Okay. Check. Now we want a formula for the total. So the total area is going to be approximately equal to the sum from I equals 1 to n. Again, we're going to let this flow. We haven't nailed down a specific value yet of this expression. 3 I over n squared times 1 over n. Check. All right. And now what we're going to do is limit as n goes to infinity of this process. So I'm going to go ahead and do this right over here. So the total area under that curve should be identically equal to limit as n goes to infinity of this expression, sum from I equals 1 to n of, and let me clean this up a little bit. Let's write it like this: 3i squared over n cubed. Now, an important point here. At this point right here, we're pretending that n is some finite number. That's why this is an approximation. It becomes identical or exact when you take limit as n goes to infinity, because the delta x goes to 0, you end up with the exact area under the curve. So now we have to figure out, how are we going to deal with this guy? Now, there's a bunch of formulas for doing these things, and in the current calculus text that we're using, I'm going to write this one down. In the book I'm using right now, it's on page 261. I'll write it over here. The sum, and it says from k equals 1 to n, I'm going to write it exactly as it is in the book, of k squared, and the reason I'm looking for k squared is we have this I squared here, right, is equal to n times n plus 1 times 2n plus 1 over 6. And again, if you're in my current class right now, that's on page 261 of the textbook we're using. And there's other formulas for the sum of k cubed and the sum of just k's on the previous page. This one's the appropriate because what we're looking at right here is the sum from I equals 1 to n of I squared. Just ignore that right now. It's about this guy right here. So let me do this in green. Sum from I equals 1 to n of I squared. Sum from k equals 1 to n of k squared. It doesn't matter that it's a k or an I. This sum is equal to, all right, so let me rewrite. So we got limit as n goes to infinity, and then 3 over n cubed, and then the thing I circled in green is equal to n times n plus 1 times 2n plus 1 over 6. Now I know there's notationally a couple little tiny things, like here it's little n. I always put big N for my limits, don't ask me why. It doesn't matter, right? They're talking about, whatever value this is, and whatever you put here, they're the same thing. And then whatever you have here, I, that's your index, here it's equal to k. So anyway, we got this expression here. Now we just have to figure out limit as n goes to infinity. All right, equals. Now if you don't mind, let me put limit as n goes to infinity. Now, this looks like a bunch of stuff we're going to have to multiply out here, but we can probably do this without multiplying this out. First of all, let's take this 3 over 6. And I know that that's 1/2, but let's just ignore, we don't need to simplify it yet. And now, when we multiply this stuff out right here, and here's what you have to focus on here, I'll do this in blue. This multiplication right here, by the time you FOIL this and then hit it with an n, that very first term is going to be 2n to the third. This is a very important part of this problem right here. Right? If you check this out, this is n squared plus n, and by the time you FOIL this, that first term is 2n to the third. All other terms are going to be smaller powers of n. I'm going to put plus something n squared, plus something n, plus a constant. Okay, these are all going to be numbers. If you want to multiply them out, feel free, but I'm not going to bother because I know we're not going to need them. Now this is all divided by n cubed. All right, so this is going to equal the limit as n goes to infinity, and I guess I'll go ahead and clean this up now, 1/2 times. Now, dividing this fraction out, this is going to be 2 plus a number over n. I'm just going to put this, a number over n, plus this term is going to be some other number over n squared. This one is going to be a number, some other number over n cubed. Pardon my laziness for not feeling like multiplying it out, but here's the part where I knew we're not going to need it. When you take the limit as n goes to infinity, that goes to 0, that goes to 0, that goes to 0. That's the only term that survives, and we end up with 2 times 1/2, which is 1. I'm going to take a moment here, calculate the exact area from methods that we're going to talk about later in the course. The exact area under that curve is x to the third. Evaluate 0 to 1, which is 1, so we're good. I know that this is done correctly. So, all right, so this video was meant to be kind of an introductory video on how to use the limit process in Riemann sums to calculate the exact area under a curve. Again, here's your processes here. Step 0, draw your rectangle, set it up very concisely. This is probably the most important step. How you draw these rectangles will dictate what your work looks like. I usually just draw them the first thing that comes to mind. Here I decided upper bounds. If you wanted to do lower bounds, that would be fine too. You'd have, basically no rectangle, and then one like this, one like this, one like this. You can use midpoints, but there's really no reason to when your game plan is this limit as n goes to infinity. Okay. You then need a formula for your x sub i's. I strongly encourage you to mark them on the page, the values that you're going to need. That will help you write the formula in this case. 1 delta x, 2 delta x, 3 delta x. It was pretty obvious what my formula was. Okay, if this one started at 0. If you weren't starting at 0 like we were starting here, it would be your formula would have to have that starting point taken into consideration. I'll just make another video on how to do that. 3, write your formula for the area of the ith rectangle. That formula should be good for any of them. It should have n's in it because you're going to let that n float. We're just not going to pick a value. We're just going to leave that be a variable in the problem. 3rd, write a formula now for the total area. Basically, you take your ith rectangle or kth rectangle, whatever you want to call it, put a summation from 1 to n in front of it. Step 4, now you take the limit as n goes to infinity. This is a very important math step because what this does is where do we go here? At this point, your area is an approximation for any given number of n. It's this limit process as n goes to infinity that makes that area exact. Now, you do your algebra, simplify it. There's really a limited number of problems you're going to be able to work this type of math on. As far as letting n go to infinity, this will usually require some of these what are called summation formulas. And again, in this calc book, they're on page 261. Take the limit as n goes to infinity, should converge to a constant. So anyway, I hope that this video was successful in helping you understand how to use Riemann sums and the limit process to calculate the exact area under a curve. Have a great day.